Hello everyone, welcome back. So today's video is based on mechanics problems. Okay, and these are going to be problems from rotational motion. So in the first question, we have an assembly of two discs, each of mass m, as shown in the figure, is placed on a rough horizontal surface. So the centers of discs A and B are connected with the help of massless rod. Both the disc can rotate freely about its center, and it's given that the friction is sufficient to sustain rolling in the rear wheel. Okay, so the rear wheel will be this wheel over here, which is wheel B. Okay, so and we have a few questions that we have to comment on. Okay guys, so this is the diagram of the situation. So initially only the front disc had a rotational speed and the back disc was at rest. Okay, now in the first question they're saying the normal force at A from the surface is equal to the normal force at B from the surface. So to comment on the normal forces, so the normal force is quite straightforward. So vertical force is, so the only forces in the vertical direction on both A and B is the normal and the weight of the ball, and the rod will just apply a tensile force on the tensile force that is in the horizontal direction. So NA and NB are both equal to just mg, so they are actually equal to each other, so option A will be correct. Okay, so B and C would be wrong, and in option D they're saying what is the direction of frictional force from B is in the forward direction till pure rolling starts. Okay, so now this is a bit this is a bit unclear here what they mean by forward direction. So we'll just use x and we'll just use either plus I cap or minus I cap to express in which direction is friction acting. Okay, so first of all, the bottommost point of disc A, it will slip towards the left, right? Because this point at this instant has a speed of r omega naught towards the left, which means it is slipping against the floor in the leftward direction. So the kinetic friction force Fk acts towards the right on disc A. Okay, so this Fk will actually accelerate the disc. At the same time, it will provide a counterclockwise angular acceleration to slow down the rotational speed. So now the thing is, we know the center of mass is going to accelerate towards the right. We know that the length of the rod doesn't change. So even the center of the disc B will have the same acceleration as the center of the disc A. So let's say that the acceleration of this disc is A. So the acceleration of disc B will also be A. Okay, so now in the question it was mentioned that friction was actually sufficient to allow rolling for the back tire, which means disc B will actually start rolling immediately after the motion starts. So now, which means if the bottommost point of disc B is not slipping, then it must have a clockwise angular acceleration, right? It definitely should have a clockwise angular acceleration such that the translational acceleration is equal to the rotational acceleration, so that the bottommost point does not slip, right? Now the thing is, if we observe with respect to the center of mass of disc B, and we want to ensure that there must be a clockwise angular acceleration, then the friction from the ground must be towards the left, because only then it can provide a clockwise torque above the center of mass, right? Because there is no other force that is providing any torque above the center of mass, we can observe. So here the direction of friction is in the minus I cap direction. Now what they meant by forward direction is unclear, so we'll just leave this option as such. Okay, so now let's talk about these options. So here in option A they're saying what is the initial acceleration of the center of mass of disc B and the value of frictional force. Okay, so this is the initial FBD of the situation, right? And it's easier to start with this disc because we know it's rolling, right? As it is rolling, we can say the acceleration A is equal to the R alpha is equal to R alpha. And now we can use the torque equation. Friction has a clockwise torque above the center of mass, so we can say friction F multiplied by the radius equals moment of inertia about the central axis times alpha. Okay, so now we can write alpha as A by R and cancel out the R's, and we'll get F equals MA by 2. So now once we know friction, Fk we clearly know it is just mu times Na, and Na was equal to mg, so this is just mu mg. Okay, so now if I take both the discs and the rod as my system, then the external forces in the horizontal direction are F and Fk, right? Fk minus F, so this is the net force towards the right, equals Ma plus Ma. Okay, so the acceleration of both the discs are A in the rightward direction, so we'll write Ma because of each of these masses, right? So now we can just put the value of F into this equation, and we'll get the initial acceleration as 2 by 5 mu g. Okay, and in fact this will be the acceleration till the front tire starts rolling as well. So option A over here is actually correct. Now the frictional value, now the friction force, we figured it out, it was Ma by 2, right? So if you multiplied the option A by ma by 2, it'll actually be correct. Now they're asking us about the linear impulse given to the disk B. Okay, so for that we have to talk about the final situation as well. Okay, so now most of these options are talking about the final situation. So let's discuss about the final situation. Okay, so finally it's quite clear that what will happen is both the disks will gain some common angular velocity. This is obviously because the front disk will also start rolling after some time, right? And when it starts rolling, we can write V equals R omega, right? And we know the velocities of the centers are the same for both the disks. So if their V's are same, then omegas should also be same in the final situation. Okay, so now how do we figure out omega? So the easiest way to determine omega is by using angular momentum conservation. But the thing is, we have to choose a point about which the net torque actually turns out to be 0, right? And a great point is a point that is on the ground somewhere over here. Let's call this point as point P. Now, why is the angular momentum conserved about this point? So in the initial diagram, so firstly observe that there is no torque of friction about this point P, because the line of action actually directly passes through point P, right? Okay, so whenever a force passes directly through the point about which we are writing the torque, its torque actually becomes 0, right? So the only other forces left are N and mg, which obviously cancel each other out, right? So the torque of N, say it is equal to N into X, then the torque of mg is going to be mg into X, but they are equal and opposite, so they cancel out. There is no other force left on the system. Because of that, we can clearly see that the net torque about this point P is actually 0. Okay, and if the net torque of the system about this point P is 0, then we can conserve the angular momentum, right? Okay, so we are going to conserve angular momentum about this horizontal axis passing through P. Now, if you observe, there is an option over here in which they are saying the same thing. The angular momentum of a system A, B, and rod about an axis passing through P and perpendicular to the paper remains constant, which is actually true. Okay, so that is basically what we discussed. In the question, they put the point P over here, but it's the same thing, right? So this option is also correct. Okay, so now let's conserve angular momentum. So for conserving angular momentum, we'll be using the result. So we'll be using this result. So the L about the point P, we can write it as M RCM cross VCM of all the masses plus I omega. Okay, so now in the initial situation, obviously this disk was completely at rest and this guy had a rotational speed of omega naught. So initially the angular momentum about the point P is, we'll just include this I omega term. Now guys, I is the moment of inertia about the center of mass of the disk, and that will be mr square by 2 and times omega naught. Okay, times omega naught. So this is the initial angular momentum and it is into the page. So now let's talk about the final angular momentum. Okay, now in the final situation, both the disks start rotating with the angular velocity of omega, and they also start translating with the velocity of center of mass v. Okay, so the velocity of center of mass, let's mark it as v. Now here, obviously guys, v will be equal to r omega because it's rolling condition, right? Okay, so now if you write the angular momentum about this point P, firstly let's write for this disk. So the this is RCM vector. So if you do M RCM cross VCM, we'll just take the perpendicular component of RCM. That is just going to be the radius R, right? So it'll be MVR. And then we have to add I omega to it. So that will be the net angular momentum of this disk about the point P. So I'm just going to directly write it in one step. So MVR plus I omega. If you do this, just comes out to be 3 by 2 MR square omega. So I substituted V equal to R omega into the MVR term and added both of them, and we get 3 by 2 MR square omega. And similarly for this disk also, the contribution is going to be exactly the same, right? Because even though RCM is further away, if you do RCM cross VCM, that will only consider this perpendicular component. It will be MVR anyway. The contribution will just get doubled. So this is going to be 3 MR squared omega. So this is the final angular momentum about the point P. Now we can just equate these two, and we can see that omega equals omega naught by 6. So the final rotational angular velocity is omega naught by 6. Okay, so what they meant is the final angular velocity or angular speed. Okay, so now in option C, they're asking us about the total linear impulse that is given to the disk B. So the disk B is over here. Okay, so that they're asking the total linear impulse. So they're asking integral of f net dt. So this will obviously be equal to the change in linear momentum of the center of mass of disk B. So initially the center of mass was at rest, and finally it gains a velocity of v, which is actually also equal to r omega naught by 6, right? So this will be m r omega naught divided by 6. So even this option is actually correct. Now in option D, they're asking the work done by friction on the disk A is negative. Okay, so here this question can be answered directly, but you have to be a bit careful because if you observe, the center of mass will start moving towards the right. So we may think that Fk is acting in the rightward direction and the center of mass is moving in the rightward direction. So the work of Fk on this disk A is actually positive, which is actually wrong. Okay, because the definition of work is that, so if you want to write the dw, or the small work by friction, it is the friction force Fk dotted with the displacement vector of the point of application of the friction force. Here the friction force is acting at the bottommost point, so we have to see how is the displacement of the bottommost point, and that, as we saw earlier, initially omega naught is very large and the center doesn't have any speed, so the bottommost point has a leftward velocity. So if we just write down the power of friction force, it will be Fk dot the velocity of the bottom point, right? And the bottom point's velocity is towards the left, Fk is acting in the right, so clearly we can see it's negative. Until when will slipping continue? It will continue till the bottommost point achieves zero velocity. So from this instant, from the starting instant till the final instant, velocity of the bottom point will be towards the left and Fk will be towards the right, so they are clearly negative. So the work done by Fk is clearly negative. Okay, so option D will also be correct. Now in option, okay, so now here they're saying the value of linear impulse given to the disk B by the rod. Now in this option they wanted the total impulse, and in this option they want the impulse by the rod. Okay, so in this F net, it includes two forces. First is the force by the rod, right? So this will be one of the impulses, and secondly it will be the force of friction or static friction that is giving the impulse. So okay, so the static friction, once again, it was in the leftward direction, right? So it's going to, impulse will be negative, right? Because it's trying to decrease the velocity of the center of mass. So, and the velocity and the impulse provided by the rod will be positive. Okay, now in the friction force on disk B, we earlier figured out it was mu mg by 5, right? So I can write down its impulse as mu mg by 5 multiplied by delta t. So delta t is a time frame basically from the initial moment till the final moment when the velocity of the center of mass becomes r omega naught by 6. Now we know the acceleration of their centers is 2 by 5 mu g, right? And we know the final velocity. The final velocity is r omega naught by 6. So we can easily figure out the time using the kinematics 1D formula, right? So r omega naught by 6 equals the initial velocity plus the acceleration multiplied by the time. So from here we get delta t as 5 by 12 r omega naught divided by mu g. Okay, so now we'll put this over here and we'll get the answer as mu mg by 5. Okay, and this just becomes mg mr omega naught divided by 12. Okay, and once again it is going to be negative because it's acting in the leftward direction, right? Which means in the impulse of the rod, which means the impulse applied by the rod is just going to be mr omega naught by 6 plus mr omega naught by 12, which is mr omega naught by 4. Okay, so this option is actually going to be wrong. Now in option D, they're saying what is the total work done by friction force on the system A, B and the rod. Okay guys, so now there is two ways to find this out. First we'll discuss the easiest way. So obviously guys, here disk B is actually rolling, right? So we don't have to worry about this friction force because it's because that's static friction force and the bottommost point is at rest, and the bottommost point has a zero speed. So basically the power of friction is zero, and you guys know that, right? So in rolling motion, static friction does no work. Okay, so the only friction that is doing any work is the kinetic friction force acting on the disk A. If you also observe, the kinetic friction force Fk is the only force which is causing a loss in mechanical energy, right? So there is no other dissipative forces in the system. So if I figure out the change in mechanical energy of the system, which is initial Ke and minus final Ke, the difference of that will give me the energy dissipated or energy lost, right? And that lost energy will be the work that friction has done. So that's the idea that we'll be using. Okay, So the change in mechanical energy of the system is final kinetic energy minus the initial kinetic energy. So finally we know both the disks are rolling, so we'll multiply it with 2, and the kinetic energy of one rolling disk we can write it as half I about the instantaneous axis times the final omega, which is omega naught by 6 squared, right? So this is the final kinetic energy. Initial kinetic energy, only one of the disks possessed an angular velocity of omega, so it'll be half mr squared by 2 times omega naught squared. Okay, so after solving, you'll get it as minus 5 by 24 mr square omega naught squared. Okay, so the final amount is less than the initial amount by this much value. And where did all this energy go? It went because of the negative work done by friction. Okay, so this is the work done by friction on the system. So this is the easiest way to find it. And another way is by just using the basic definition of work. So we'll do force of friction times the displacement of this point of application. Okay, and there is like two methods that you can use here. So one method is by using kinematics. So you can say this has a translational acceleration of A and the rotational R alpha acceleration, right? And with this, find out the net acceleration and then find out the net displacement of the bottommost point. And after that, it's just Fk into the displacement, right? Or you can use the formula of power. So we can write down the instantaneous power dissipated by friction. So this will be minus Fk dot the velocity vector of the bottommost point, right? So the Fk is going to be mu mg. Okay, so there won't be a minus here. Fk is mu mg towards the right. And let's find the velocity vector. Right, so the velocity of the bottommost point will be a linear combination of the velocity v and r omega, right? So I'm going to write it as v minus r omega. Okay, so so friction is in the right direction, v minus r omega is in the right direction, therefore the dot product is positive. So now this will be mu mg. Now the velocity v we can write as the acceleration multiplied by the time, right? And the acceleration was 2 by 5 mu g. And the time is t. Now omega as a function of time is a bit different. So initially it was omega naught, and we have to minus alpha t from this because if you observe, the angular acceleration is counterclockwise, right? So it's decelerating the omega. So we can quickly find the angular acceleration of disk A. So Fk into r will be equal to mr square by 2 into alpha. And from here alpha just turns out to be 2 mu g by r. Right, so now we'll substitute 2 mu g by r into alpha. So after that we'll get the power of friction as a function of time, right? And now we know the power is just the rate at which work is done. So with that we can say we can write dw friction as p dt, and we can just integrate it from 0 to delta t, and this will give us the work done by friction as well. Okay, so I'm skipping this method. You guys can try it as a homework. Okay, so these are two ways in which like you can solve the work done by friction part. So yeah, that's about it for this question. Now let's move on to another question. Okay, so in this question we have a uniform cylinder whose mass is m and its radius is r, and it's rolling without slipping on a fixed rough cylindrical surface of radius capital R. Okay, so it's rolling on this surface basically. So the bottommost point has a 0 velocity. At a certain instant, the line OC has an angular velocity and an angular acceleration. Okay, so basically this line is rotating with some angular velocity omega, and it also has an angular acceleration of alpha. Okay, so then the first question is asking us what is the acceleration of point P, which is this point of the cylinder. Okay, so this is not the point on the ground. This is the point on the cylinder, which is at its base. So we want to figure out its acceleration with respect to the surface. With respect to the surface just means with respect to the ground frame, right? So basically we have to find the ground frame acceleration of the bottommost point of the cylinder. Okay, so that is what these three questions are asking us. And in option D, they're saying the tangential acceleration of point P with respect to the surface is leftwards. This is actually not true, because if it was because we know it's rolling without slipping, right? So its tangential acceleration at this instant, it has to be 0. Okay, so option D is clearly wrong. So now let's talk about the acceleration of point P. Okay, so firstly, this line had an angular velocity and an angular acceleration, and the line's name was OC. Now guys, this cylinder is rolling on the larger cylinder, so even this guy will have some angular velocity. So we can call that as capital omega. Okay, and even this guy will have some angular acceleration. We can call it as ohm dot. Okay, ohm dot means d omega by dt. Okay, so this is the angular velocity of the cylinder, angular acceleration of this cylinder about its own axis. And this is the angular velocity and angular acceleration of this line OC. Now this distance is smaller and the pink, and this distance is capital R. Okay. Now guys, if I know the angular velocity of this line, then I can write the velocity of point C as the angular velocity multiplied by the distance from the axis. So the axis is at O and the distance from the axis is capital R plus small r, right? So it is going to be omega times capital R plus small r. So the velocity of the center is small omega times capital R plus small r. Okay. Now what is the rotational speed? Now what is the speed due to rotation of the cylinder at the bottommost point? So the angular velocity of the cylinder is ohm. So the rotational speed at the bottommost point is going to be ohm multiplied by r, right? Now if we superimpose the velocity of the center, they should cancel each other out, right? Only then the point P will have a zero velocity. So from here we get ohm as small omega times 1 plus capital R by small r. Okay. So we now figured out ohm. Okay. So now if we just differentiate it, we can also figure out ohm dot, which is going to be alpha times 1 plus capital R by small r. Okay. So now we wanted the velocity of the bottommost point of the cylinder. Okay. So it's clear that it won't have any tangential acceleration because of the no slip condition. Okay, so first let's observe with respect to the center. So imagine that the center is hinged for a second. Now if the center is hinged for a second, we'll only observe the rotational speed of omega, right? The center of mass is not translating anymore like in this case. So in this case it was translating in a circle, right? So now we are observing with respect to the center of mass. So now we'll only observe a rotational motion of angular velocity of ohm. In this case, we know each and every point will move in a circle about the center of mass. So the bottommost point will move in the outer circle of radius capital R. So this particular point P over here, it will have a centripetal acceleration towards the center of mass, whose magnitude is the angular velocity squared multiplied by the distance from the axis, which is small r. Okay. So this is a centripetal acceleration of point P. So what we figured out here is the acceleration of the point P with respect to the center, and this turns out to be ohm square r in the j cap direction. Okay. Now we know how relative velocity works. If we want the acceleration of this point P over here, then we need to find the acceleration of point C, right? Once we find the acceleration of point C, we'll add them vectorially and we'll basically get rid of the C, right? And then we'll get AP with respect to ground. Okay, so for that, let's see how C is moving. So C is over here. Now this point C is actually moving in a circle, right? This length CP is a constant, right? So this length C, so this point C is actually moving in a circle whose radius is capital R plus small r. So whenever a particle is moving in a circle, it has two components for acceleration. Okay, so we know C is moving in a circle about the point O. So it will have a centripetal acceleration of omega square r. Now, here you have to pay attention. The circular motion of center of mass, the angular velocity with which it is moving is small omega, right? Okay, so now because of the circular motion of C, it will have two components of acceleration. One component is towards the center of curvature, which is point O, and the magnitude is going to be omega square because the angular velocity of this circular motion is omega, right? So it will be omega square times distance from the axis, which is capital R plus small r. So if this is C and this is O, circular motion is of radius capital R plus small r and angular velocity is small omega. So the acceleration is towards the center and has a magnitude of omega square capital R plus small r. Okay, and it will also have an alpha component, right? Which will be capital R plus small r times alpha. But we can ignore this in our discussion because we are just interested. We already know that P won't have any tangential acceleration, right? Okay, so the acceleration of C with respect to the ground frame, I'm just considering the vertical acceleration or in the y cap direction. Okay, so this is equal to omega square capital R plus small r in the minus j direction. So now all we have to do is add the relative acceleration to AC. So AP is going to be AC vector plus AP with respect to C vector. So this will be ohm square r minus omega square capital R plus small r. So now we'll substitute the value of ohm into this equation. Okay, so if you remember, okay, so after solving, we'll get the answer as this particular value. Now here, if you observe, we took the upward direction as positive. So this is in the upward direction. Okay, so that actually corresponds to option A, and the direction is radially outward. Now the next question they're asking us about the kinetic energy. Now the kinetic energy, we can write it in two ways. First is half mvcm squared plus half I about center of mass times omega squared. Or what we can do is use the instantaneous axis of rotation, because that is just this contact point over here. So the kinetic energy is just directly going to be half I about the instantaneous axis. So this is a solid cylinder, so it is going to be 3 by 2 mr squared times the angular velocity of the rigid body, which was ohm squared. Okay, so this will be omega square 1 plus capital R by small r squared. Okay, and actually A and B doesn't match with this option. So let's read option C. So in option C, they're saying the magnitude of normal reaction between the cylinder and the surface is less than the weight of the cylinder. Okay, so we have to talk about F equal to ma in the normal direction, right? So now once again, guys, the acceleration of the center was in the downward direction, right? The center of mass, which means mg definitely should be, which means mg is clearly greater than normal, right? Only then there will be a acceleration in the downward direction. Yeah, mg is clearly greater than normal, or in other words, normal is less than the weight. So option C is actually correct. So answer to this part will be option C. Okay. So yeah, that was it for this video, guys. If you enjoyed the video, please do like, share and subscribe. And that's it. Thanks for watching.